Inside a sealed laboratory in Houston, there is a single grain of dust that shouldn't exist. It was pulled from the surface of Asteroid Bennu, a rock that has been orbiting the Sun for 4.5 billion years. But when scientists analyzed this specific speck under an electron microscope, the timeline broke. This dust is older than the asteroid it was found on. It is older than the Earth. It is older than the Sun. You are looking at a pre-solar grain. It is a microscopic piece of shrapnel from a star that exploded and died before our solar system was even born. It survived the formation of the Sun, dodged the creation of the planets, and waited in the dark for 5 billion years. We sent a billion-dollar mission to space to find the origin of our solar system. We came back with something that predates it. To understand why this specific grain of dust is so important, we first have to understand the bucket we use to scoop it up. Under the leadership of principal investigator Dante Loretta from the University of Arizona, NASA launched the OSIRIS-REx mission in 2016 with a singular, obsessive goal: bring back a piece of the early solar system that had never been touched by the Earth's atmosphere. We have thousands of meteorites in museums, but they are all contaminated crime scenes. They scream through the atmosphere, burn up at thousands of degrees, smash into the ground, and sit in the rain for decades before someone picks them up. We needed something pristine. We needed to go to the source. The target was asteroid 101955 Bennu, a near-Earth asteroid approximately 490 meters in diameter. Bennu follows an elliptical orbit with a semi-major axis of about 1.126 astronomical units, placing its average orbital distance slightly beyond Earth's. At perihelion, it approaches the Sun to roughly 0.90 astronomical units, causing it to periodically cross Earth's orbital path. NASA didn't pick Bennu by throwing a dart at a star chart. They picked it because it is a B-type asteroid. In the spectral classification of asteroids, the vast majority are S-type, stony, or M-type, metallic. But B-types are rare, dark, and carbon-rich. They are essentially black chunks of the primordial construction debris left over from the formation of the planets. If Earth is a finished house, Bennu is the pile of bricks and dry cement left in the backyard. But when the spacecraft actually arrived at Bennu in 2018, the scientists realized they had a problem. Based on thermal models from Earth telescopes, they expected Bennu to be covered in ponds of fine-grained sand, smooth beaches of regolith that would be easy to scoop up. Instead, they arrived at a world that looked like a construction site disaster. The surface was a chaotic mess of massive, jagged boulders. There were no beaches. There were no smooth ponds. It was just rock on top of rock. Several times, the mission observed rocky particles ejecting from the surface, some escaping into space, others briefly orbiting before falling back. This confirmed that Bennu is what astronomers call a rubble pile. It isn't a solid rock like the bedrock under your feet. It is a loose collection of gravel and debris held together by nothing but its own weak gravity. The density of Bennu is incredibly low, about 1,190 kilograms per cubic meter. For context, solid rock is usually around 3,000. This means Bennu is roughly 50% empty space. It is a flying mountain of gravel that is barely clinging together. If you spun it just a little bit faster, the centrifugal force would overcome gravity and the entire asteroid would drift apart into a ring of dust. This terrified the mission planners. The sampling mechanism, called TAGSAM, Touch and Go Sample Acquisition Mechanism, was designed for a sandy beach, not a boulder field. It looked like an oversized car air filter on the end of a long pogo stick. The plan was to gently tap the surface, blast a jet of high-pressure nitrogen gas into the ground, and catch the dust that flew back up. But with boulders everywhere, there was no safe place to land. The team spent 2 years mapping the surface in excruciating detail, finally identifying a tiny crater named Nightingale that was just barely wide enough for the spacecraft to descend into without smashing its solar panels. On October 20th, 2020, OSIRIS-REx went in. The contact lasted less than 6 seconds. When the tagsome head hit the surface, something strange happened. The rock didn't act like a rock. It acted like water. The surface offered almost no resistance. The arm plunged half a meter deep into the asteroid before the thrusters fired to back away. The nitrogen gas blast worked almost too well. It fluidized the surface material, blowing a massive cloud of rocks and dust into the collector. The sample container was so full that it actually couldn't close properly. Rocks were wedged in the seal and precious dust was leaking out into space. But they managed to stow it, seal it, and bring it home. And when they finally opened that canister in Houston, inside that chaotic mix of gravel and dust, they found something that changed the timeline of the solar system. When the sample canister was finally opened, the analysis began at the molecular level. The team was looking for something specific. They were hunting for pre-solar grains. In the standard model of solar system formation, the early universe was a chaotic place. A massive cloud of gas and dust collapsed under its own gravity to form the sun. This process generated immense heat and pressure. It acted like a cosmic blender. It took all the raw materials from the surrounding galaxy, melted them down, mixed them up, and homogenized them into a standard chemical soup. This is why everything in the solar system, from the Earth to Mars to your own body, shares roughly the same isotopic fingerprint. We are all made of the same mixed batch of stardust. But occasionally, a tiny speck of material survives the blender. These are pre-solar grains. They are microscopic crystals that formed in the cooling outer layers of dying stars long before our sun was born. They drifted through the interstellar medium, entered our solar nebula, and somehow managed to stay cool enough to avoid being melted down. They were locked inside the first rocks that formed, effectively frozen in time. Finding one is rare. In a typical carbonaceous chondrite meteorite found on Earth, pre-solar grains make up only a few parts per million of the total mass. But Bennu was different. When researchers analyzed the insoluble residues from the Bennu samples using mass spectrometry, they found an abundance of isotopic anomalies that defied the standard solar mixture. Specifically, they found a distinct excess of silicon carbide. Silicon carbide is a hard, refractory mineral that is incredibly rare on Earth, but common in the outflows of carbon-rich giant stars. The identification comes down to isotopes. An isotope is a version of an atom with a different number of neutrons. In our solar system, the ratio of carbon-12 to carbon-13 is fixed. It is a known constant. But inside these silicon carbide grains, the ratios were wildly off the charts. They contained isotopic signatures that simply cannot be produced by the chemistry of our sun. They matched the nuclear fusion signatures of specific types of asymptotic giant branch stars and type II supernovae. This tells us exactly where Bennu came from. The high concentration of these specific supernova-derived grains suggests that the parent body of Bennu did not just form in a random patch of the solar nebula. It formed in a region that had been recently polluted by a nearby star explosion. Imagine a pristine snowfield. If you find a patch of snow that is covered in soot and ash, you know that a fire burned nearby recently. Bennu is that patch of snow. It captured the fallout from a stellar death that happened 4.5 billion years ago. The density of these grains is the key variable here. The samples from Bennu showed significantly higher abundances of these supernova grains compared to the meteorites we have in our collections on Earth. This suggests that our meteorite collections are a biased sample. The rocks that survive the fall to Earth are the tough ones, the ones that have been heated and compressed. Bennu, however, provided us with the fragile, unaltered reality of the early solar system. We're looking at direct samples of the feedstock that built the sun. These grains are the raw ingredients. The fact that they survived inside Bennu means that the asteroid never got hot enough to melt them. It has remained a cold, dead freezer for billions of years, protecting these delicate crystals from thermal destruction. This discovery moves the timeline of the sample back. We are no longer studying the geology of an asteroid. We are studying the nuclear physics of a star that died 5 billion years ago. While the pre-solar grains gave us a window into the death of stars, the organic analysis of the Bennu samples opened a window into the origins of life. The scientists expected to find carbon. Carbon is common in the universe, but they did not expect to find what looked, for all intents and purposes, like space gum. Scattered throughout the sample were these strange, distinct globules of organic matter. NASA scientists have described this pliable, amorphous material as space gum. When viewed under high-resolution imaging, they stood out against the jagged, crystalline background of the minerals. They were not brittle, they were not hard, they appeared to be soft. This material is a complex organic polymer. It is primitive organic matter that has evolved beyond simple carbon chains into something more structured. The analysis showed that these globules are rich in nitrogen and oxygen. This is a critical distinction. Simple hydrocarbons like methane are just carbon and hydrogen. But when you start integrating nitrogen and oxygen into the structure, you are building the scaffold for biochemistry. The team found high concentrations of specific biological precursors. They identified a suite of amino acids, which are the building blocks of proteins. But even more significant was the detection of sugars. They found glucose. This is the basic fuel of life as we know it. They found ribose. This is the sugar molecule that forms the backbone of RNA. Finding ribose on an asteroid is a massive discovery. RNA is widely believed to be the precursor to DNA in the evolutionary history of life on Earth. The RNA world hypothesis suggests that before single-celled organisms existed, self-replicating RNA molecules dominated the primordial soup. The fact that the structural component of this molecule exists on a rock that has never touched a planet suggests that the Lego blocks of genetics are not unique to Earth. They are being manufactured in space. The surprises did not stop at sugar. The sample was also rich in a specific mineral called magnesium-sodium phosphate. Life on Earth requires 6 main elements: carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus. Of these 6, phosphorus is the hardest to find in a bioavailable form. It is usually locked up in tough, insoluble minerals like apatite. But the phosphate found on Bennu is water-soluble. It dissolves easily. This is the exact type of phosphate that early life would need to build DNA backbones and cell membranes. The presence of this soluble phosphate, combined with the ribose and the space gum polymers, paints a radical picture of Bennu's history. It suggests that the parent body of this asteroid was not just a dead rock, it was a warm, wet, active chemical factory. Billions of years ago, water flowed through the cracks of that parent world. That water facilitated chemical reactions between the minerals and the carbon. It synthesized sugars. It liberated phosphates. It built complex organic polymers. Bennu did not just deliver the ingredients for life to Earth, it cooked them first. This changes the way we view the asteroid bombardment of the early Earth. We used to think asteroids were just delivery trucks carrying raw elements. Now we know they were more like mobile laboratories. They might have arrived on the surface of the young Earth, already carrying the pre-assembled components necessary to start the biological machinery. The space gum is the physical evidence of this process. It is the residue of a prebiotic chemistry experiment that has been preserved in a vacuum for 4.5 billion years. The presence of both the presolar grains and the organic soup creates a geological paradox. On one hand, we have the space gum and the phosphates. These materials require water to form. They tell us that Bennu's parent body was a hydrothermally active world. It was a place where ice melted into liquid water, flowed through the rock, and triggered chemical reactions that turned dry olivine into wet clay. This process is called aqueous alteration. The vast majority of the sample mass consists of these phyllosilicates, or clays. This confirms that at some point in the deep past, the rock that makes up Bennu was effectively mud. On the other hand, we have the pre-solar grains. Silicon carbide and the other delicate stardust crystals are extremely fragile in the presence of hot water. If you expose these grains to a hydrothermal system for millions of years, they should oxidize, they should break down, they should be destroyed. Finding pristine stardust inside a rock that was once wet mud is physically contradictory. It is like finding a dry ice cube sitting inside a pot of boiling water. The solution to this paradox lies in the physical structure of the asteroid itself. Bennu is not a monolithic slab of rock. It is a breccia. In geology, a breccia is a rock composed of broken fragments of minerals or other rocks cemented together by a fine-grained matrix. It is a mosaic. When the scientists examined the samples under high magnification, they realized that the material was not uniform. While the matrix or the background material was heavily altered by water, there were distinct chunks of rock embedded within it that looked completely different. These are called clasts. Recent studies show that these clasts preserved higher concentrations of organics and presolar grains, shielding them from alteration. These clasts are survivors. The leading theory is that the parent body of Bennu was a chaotic environment. Imagine a massive collision in the early solar system. A large, wet, differentiated protoplanet gets smashed by a smaller, dry impactor. The debris from this collision flies out into space and then slowly reaccumulates under gravity to form a new rubble pile. In this chaotic reassembly, chunks of the wet, clay-rich material from the planet's interior were mixed with chunks of the dry, unaltered crust, or the dry impactor itself. The result is a geological Frankenstein. The samples returned by OSIRIS-REx contain these dry, xenolithic clasts. Xeno meaning foreign and lithic, meaning rock. These are chips of material that escape the aqueous alteration process entirely. They remain dry. They remained cold. Because they were sealed inside the clay matrix, they were protected from the vacuum of space and the radiation of the sun. But because they were distinct from the matrix, they never interacted with the water that altered the rest of the rock. This is how the stardust survived. It was locked inside these pristine pockets. This dual nature is what makes the Bennu sample so valuable. If we had gone to a completely dry asteroid, we would have found the stardust, but we would have missed the prebiotic chemistry and the space gum. If we had gone to a completely wet asteroid, we would have found the organics, but the water would have erased the record of the pre-solar history. Bennu gave us both. It provided a sample that spans the entire history of matter in our region of the galaxy. We can examine 1 micron of the sample and observe the chemical reactions that lead to life. We can move the microscope 2 millimeters to the left, look at a dry clast, and see the nuclear ashes of a star that died 5 billion years ago. The asteroid is not just a rock. It is a museum collection where the exhibits from different eras have been smashed together and fused into a single object. When we look at the OSIRIS-REx mission in its entirety, it is easy to get lost in the engineering. We focus on the rocket launch, the orbital mechanics, the touch-and-go maneuver, and the heat shield surviving re-entry. These are incredible technical achievements. But the true magnitude of this mission is not about where we went. It is about when we went. By bringing these samples back to Earth, we have effectively collapsed 5 billion years of history into a single moment. Consider the trajectory of that single grain of silicon carbide. It began its existence in the crushing interior of an asymptotic giant branch star, forged by nuclear fusion reactions that took place billions of years before Earth existed. When that star died, it exhaled this grain into the void. It drifted through the interstellar medium, a microscopic crystal floating in absolute darkness, perhaps for hundreds of millions of years. It witnessed the collapse of our local nebula. It saw the ignition of the sun. It survived the violent accretion of the protoplanetary disk. It was locked inside the parent body of Bennu, buried in mud, shattered by a collision, and reassembled into a rubble pile. It sat there, unchanged and silent, while life began on Earth. It was there while the oceans formed. It was there while the dinosaurs rose and fell. It was there while humanity learned to build fire, then cities, then rockets. And finally, after all that time, a species made of that same stellar dust built a machine, flew it across the solar system, picked it up, and brought it home. The connection is intimate. The analysis of the space gum and the phosphates tells us that the boundary between us and space is an illusion. The distinct separation we feel between the biology of Earth and the geology of asteroids does not exist. The phosphates that make up the backbone of your DNA and the ATP that powers your heartbeat are identical to the soluble phosphates found in the Bennu clays. The ribose necessary for your genetic code is the same molecule found in the organic residues of the asteroid. We used to ask if the ingredients for life existed elsewhere in the universe. Now we know that the universe is saturated with them. We know that the chemical pathways that lead to biology are not a fluke that happened once on a wet rock near the sun. They are a fundamental manufacturing process of the solar system itself, baked into the clay of the asteroids that rain down upon the planets. The OSIRIS-REx samples have transformed planetary science. For centuries, astronomy was a remote discipline. We could only look. We could study the light from stars and the reflection from asteroids, but we could never touch them. Now, we have entered the era of direct contact. We can put the early universe under a microscope. We can slice it with ion beams. We can measure its isotopes. We went to Bennu to answer questions about the origin of the solar system. We returned with answers about the origin of ourselves. When the scientists in Houston look at those tiny, glittering grains of pre-solar dust, they are not just looking at a rock. They are looking at the ashes of the stars that died so that we could live. They are looking at our own prehistory, preserved in the cold vacuum, waiting for us to come and find it.